Good morning, everyone. A very good morning. Shall we begin the session? Today's topic is the same, that is a revision of computer system. Yes, that is allocating a page. So this figure shows the effect of an example when the operating system uses. This includes some malloc function, calloc function, what are the various categories that is used in the malloc, calloc that is available under there. So this uses the malloc function, calloc function, and so on. So allocating the pages that is used with the operating system, that allocating a new page of the virtual memory, for example, as a result of the calling function malloc, this uses a new kernel page that is used with the kernel allocates with the physical page with the PTE physical page number, that is a kernel that also allocates the various resources that is used with this one, that is available with the memory resident page table, that is a data that creates a room on the disk and updating this one. Alright. On locality to the rescue again, that means we are using the rescue again with the disk, with the virtual memory, with the null values, with the BP1, BP2. When many of us learn about the idea of the virtual memory, our first impression is often that must be terribly efficient or inefficient, and given the large missed penalties, we worry that paging will destroy program performance. In practice, virtual memory works well mainly because of our old friend locality. Old friend locality in the sense, whatever the terms we are using, whatever the doubts we are using, that is terms is available under the locality, that is used with the active pages, that is used with the physical memory, working set, or the resident set. And after an initial overhead, whatever the overhead we are using, where the working set is paged into the memory, subsequent references to the working set results in the hit with no additional disk traffic. And we are using the thrashing, then the program can produce an unfortunate situation such as a thrashing where the pages are swapped in and out continuously, and whenever we are using the virtual memory, that is usually inefficient. If a program performance slows to crawl, the wise programmer will consider the possibility that it is thrashing, it is going down. Then next is VM as a tool for memory management, that also supported similar than the available physical memory, that is used with the virtual memory. That was still a useful mechanism that we are using because it has greatly simplified memory management and provides a natural way to protect the memory. So memory management is to, yes, it's to verify or simplify the memory that is available with the virtual memory, that is available with the mechanism that is spreaded or that is greatly spreaded among the memory management among the provided way or the natural way to protect the memory. And the combination of the demand paging and the separate virtual address space has profound impact on the way that memory is used and managed in the system. And in particular, VM also simplifies the linking and the loading, that is the sharing of the code and the data, and the allocating the data to the memory. Allocating the data in the sense, whatever the data we are using, whatever the scenario we are using, that is allocating the data or map to the physical pages. And the combination of the demand paging and the separate actual or virtual address space has been profound impact on the way that the memory is used and managed in a system. And in particular, VM also simplifies the linking and the loading, the sharing of the code and the data, and the allocating the memory to the applications. First point is simplifying the linking. Whenever we are simplifying the linking, so there is a separate address space that allows each process to use the basic format for its memory image, regardless of where the code and the data actually resides in the main memory. For example, every process on a given Linux system has a similar memory format that is used. Always starts with a virtual address that is used with a 32-bit address space, and the data have sections or BSS section follow immediately after the text section, and the stack occupies the highest portion of the process address space and also grows downwards. Such uniformity greatly affects or simplifies the design and implementation of the linkers that allows them to produce fully linked executable that is used with the simplifying the library, that is used with simplifying the locations. Then simplifying the loading, one is the linking, one is the loading that loads the executable and the shared file that is used with the sections ELF executable that are contiguous. And the notion of or this notion of the memory or this notion of the memory that is used as a set of the contiguous memory location to an arbitrary location in arbitrary file that is known as a memory mapping. And Unix also provides a system call known as mmap that allows application programmers to do their own memory management or memory mapping. That we will describe the application based or application level memory mapping in more detail in this one. And then simplifying the sharing. So separate address spaces provides an operating system with a consistent mechanism for managing the sharing between user processes and the operating system itself. And in general, every process has a separate area, every process have a data, every process have a scenario that is available that is not shared by other processes. And in this case, the operating system also creates a page table that maps the corresponding page table, corresponding virtual pages to disjoin the memory, to disjoin the physical pages. That is also available or desirable for the process to share the code in the data. The next is simplifying the memory allocation. This also simplifying because everything is, yes, everything is separate that requires the heap source, that is the result of the calling the process malloc. Operating system allocates an appropriate number, say k, of contiguous virtual memory pages and map them to the k arbitrary physical pages located anywhere in the physical memory. And because of the way page table works, there is a need for the operating system to locate k contiguous pages of the physical memory. And these pages can be scattered randomly in the physical memory. Then VM as a tool for the memory protection. Yes, it is used as a memory protection for selling out, for taking out the CPU trigger. That is also a general protection for that transfers the control to the exception handler in the kernel. The next is address translation. That is how to, yes, how, how the address will be translated, how the appreciation of the hardware role in supporting virtual memory with enough details so that you can work through some concrete example by hand. However, keeping in mind we are omitting a number of details, especially relating to the timing that are important to the hardware designer, but are beyond our scope. That is beyond our scope with the memory management, with the rule regulation. And for your support, we are using the memory management, that is 2 power n, that is the number of addresses in the virtual address space, then 2 power m, that is the number of addresses in the physical address space, then page size, that is the bytes. Then virtual page offset, bytes, virtual page number, TLB index, TLB tag, that is again used with the physical page offset, byte, physical page number, byte offset, that is also used within a cache book, cache index, cache tag. Then this is a map. This is west, PS, UV. Then A dash, virtual address A that is present at the physical address A dash. Then virtual address A that is not present in the physical memory, that is used with the page table base register, that is PTBR, points to the current page table. That has a two complements or components, p-bit virtual page of page offset, that is VPO, and -1, that is a VPN. And these are the various steps that the CPU hardware performs when there is a page hit. And whenever we are using the operational view of the page hits and the page fault, that is also available with the physical address, that is also available with the page table, yes, page table exceptions handler. Then yes, these are the various problems that is given over here. Then next is integrating the caches and the VM. That is, integrated means combining the cache memory as well as the VM memory. That also shows a physical address cache that might be integrated with the virtual memory. That might be integrated with the virtual memory, and the main idea is that the address translation occurs before the cache lookup, and that is also used with the speed up, that is also used with the address translation, that is used with the small cache of the PTE, that is known as the translation look aside buffer, TLB. And TLB hit, TLB miss, that is also used with the address translation steps.
So there are multiple steps. Step number 1 is the CPU generates a virtual address. Step number 2 is the MMU fetches the appropriate PTE from the TLR. Then step number 4, yes, step number 2 and the 3 are the same or including in one part. Then step number 4 is MMU translates a virtual address to a physical address and sends to the cache memory. Then cache memory also returns the requested data word to the CPU, Central Processing Unit. The next part is multi-level page table. That is how to use a multi-level page table that takes the 32 bits or the 4 KB pages. And the direction if we are using or whatever the direction we are using for the page table that is computed or that is compounded for the system with the 64-bit address spaces. And the common approach for compacting the page table is to use a hierarchy of the page tables instead. And the idea is easiest to understand with a concrete example. And consider a 32-bit address space that is partitioned into the 4 KBs or the 4 KB pages with the page table entries that are the 4 bytes each. And suppose that at this point in time, the virtual address space has the following form. The first 2 pages of the memory are allocated for the code and the data. Next k pages are unallocated. Next 1023 pages are also unallocated, and the next page is allocated for the user stack. And figure 9.17 also shows that how we use or how we might construct a 2-level page table hierarchy for this virtual table or for this table that is available under this or that is available under the address space or the virtual address space. And each PTE in the table has also affected with the chunks with the usage that is available with this. So whatever the data we are using, that is available, that is used in this one, that is used in so that is available with the 1024 contiguous pages. For example, PT0 map that is available with the data for the chunks, address space is 4 GB, 1024 PTE, and if every page is unallocated, then the level 1 PTE is also null. For example, this is used with the 227 or chunks are unallocated. This is if at least one page in chunk I is allocated, then level 1 PTE point to the base of the level 2 page table. For example, if I'm talking about the figure 9.17, all of the portion of the chunks 0, 1 and 8 are allocated with the chunks with the PTE up to the 2 page table with the TLB, with the PTE, with the cache memory. And each PTE in a level 2 page table is responsible for mapping a 4 KB page of the virtual memory. Just as we looked at a single page table, notice with the 4 byte memory with the VPO with the PTE 0, 1, 2, null, that is 2 page table or the 2 level of the pages that is available over here or that is used over here with the 2. Whenever we are using the end-to-end address translation, that is used with the TLB, that is used with the L1 T cache, and that is kept in mind with the byte addressable with a memory access to the 1 byte words. And the virtual addresses are the 14 bits wide, 12 bits wide, 64 bytes, and TLB is a 4-way set associated with the total 16 total entry that is used with the 4 byte lines size and the 16 bits that is used with the TLB, VPN, virtual page number, virtual page offset, physical page number, physical page offset that is used with the PPN valid, that is used with the PPN valid tags, PPN 2D, then TLB1, then 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 till 30. Then CT, CI, CO, that is used with the PPN, that is used with the PO, that is used with the PPO. Then index, then tag, then there is a valid tag, bulk 1, bulk 2, bulk 3, that is 0, 1, 2, 3. And this is used with the TLB and so on. And page table TLP we have done already. This we have done. Now case study we have already done in this. Then memory mapping we have done. So we are finished with this, we can say, this module. Now in the next class, listen, that is in the Monday's class, I'm going to start with the revision of the database design concepts, not the revision of it, because we have taken lots of time as per your requirement, because the requirement is that computer system is very tough module. So please focus on this one, or please give more time on this one. In the previous also, in the revision also, to have given the more time, but from Monday onwards we will